Hello. Today we're going to look at, well, the next three videos are going to concern an application of the integral called volumes of solids of revolution. And the idea is that we can take an area, for example, something looks like this, and we can rotate this area, and for us I'm just going to consider rotation around an axis, and you'll have to forgive my picture here when I do these rotations in 3 dimensions, but we're going to get something that looks like this in this particular case with, so it's 3-dimensional, and we're going to get this volume. We're going to get this 3-dimensional object, and the idea is we want to find the volume of that object. So we might take this particular area, and if I rotate about the x-axis, it might look like something like this. If I were to take this same area and rotate it around the y-axis, it might look something like this. And again, you're going to have to use somewhat of your imagination. We have the axis of rotation. Kind of goes right through this. The middle. And this is an open space in the middle, and so you would have this kind of hollowed out. And there are actually 3 different methods depending on the shape and the axis that we rotate. This would be rotated around the y-axis. There are actually 3 different methods that we can use. The 3 methods are called the disk method, the washer method, and the shell method. And so this video is going to deal with the disk method. The disk method is what happens when I take this first kind of situation, and when I rotate that, I get, if I were to slice the 3-dimensional object that I get after I do the rotation, I get a circle or a disk. And again, you have to forgive my drawing here, but this sliced, this rectangle that gets rotated forms a circle, and so when I slice it, it becomes a circle or a disk. And basically the idea in this particular situation is you can think of this as kind of stacking up infinitesimally small circles next to each other, until we get the object that we are dealing with. And again, looks something like this. But think of these as stacking one circle next to another kind of deal. Okay, so let's move to some examples of the disk method. Let's start off with y equals the square root of x minus 3, y equals 0, x equals 7. This area, it's bounded by these curves, and I want to rotate it about the x-axis. And so you should know what this kind of looks like. This is the square root function just shifted kind of to the right 3 units, and y equals 0, of course, is the x-axis, and when x equals 7 is the vertical line down here. This is actually the important picture that we need, the picture that involves the area. We don't really need the picture that gives us the 3-dimensional rotation. I will kind of draw it in this particular case. Generally, I'm not going to draw it because, again, I am terrible at it. So, but this is kind of this particular situation. This is the important part. And when we are, notice that when I rotate this, again, I get a circle or disk. When we do the disk method, because my result is, well, the disk method occurs, let me start here. Disk method occurs when my rectangle that gets rotated, that forms the disk or circle over here, when the rectangle is perpendicular to the axis of rotation, which is what occurs here. This is my axis of rotation. My rectangle is perpendicular to that, and the rectangle always goes to the axis. Rotation. Wherever I put my rectangle, it always goes to this axis of rotation. When that happens, we end up with the disk method. And the volume using the disk method has the form, basic form, pi integral r squared. The area of a circle is pi r squared. We integrate that circle as we move, in this case, across to get our third dimension and get the overall volume. Okay? So, in the situation like I've drawn here, my variable is x, and we are doing the area according to vertical rectangles. And so in this particular case, my volume is the integral from, my starting point was at 3, x equals 3, to 7, pi, my radius, would be the height of the rectangle, which in this case is the square root of x minus 3, quantity squared, and so this is actually very simple. Pi, the integral from 3 to 7 of x minus 3 dx, 1/2 x squared minus 3x evaluated from 3 to 7, which then becomes pi times 49 halves minus 21 minus 9 halves minus 9, which in this case comes out to be 40 halves, which is 20, minus 21 plus 9 is minus 12. And so we end up with 8 pi. Okay, generally, again, I'm not going to finish these out. Let's look at another example. Suppose I have y equals x cubed. This is the area that I want to rotate. X equals 0, y equals 8, and this time about the y-axis. And so my picture looks like this. I don't need the bottom half. This is the cube function. X equals 0 is the y-axis, y equals 8. So this region, I'm going to rotate this around the x-axis. My rectangle, when I draw that in, looks like this. And again, I'm not even going to draw the other. But notice this rectangle, as I slide it, will always touch the axis of rotation. So we are going to get a volume that involves disks, the basic form, pi r squared. Now in this case, because my rectangle goes sideways, we have to use the variable being y. And so when I write this, this goes from y equals 0 to 8. And my radius is now the distance to the curve, the length of this rectangle. Now my curve, my function is y equals x squared, but the variable is y, so I have to switch this. This becomes x is equal to the cube root of y. Remember we talked about this in the previous video. The variable on the inside has to match the limit, so I can't use x cubed in here. This would be the cube root of y, quantity squared dy, and now everything matches up nicely. This would be pi times the antiderivative of y to the 2/3 would be, add 1, you get 5/3, reciprocal 3/5. Going from 0 to 8, and then we can, this is a 5. You can calculate that out. Again, I'm going to skip that part of it. A couple more examples. Suppose I have y equals 6 over x minus 1, x equals 0, y equals 3, y equals a half, about the y-axis again. So the picture, this is the area bounded by this. 6 over x minus 1 is basically 6 over x, which is just shifted 1 unit. It's kind of 1 over x, except stretched. X equals 0 is the y-axis. Y equals 3, y equals a half. This is the region that I'm rotating. Notice, if I take a rectangle perpendicular to the axis of rotation, this is my rectangle. Let me draw that in a different color. This is my rectangle. Notice, perpendicular to the axis of rotation, that rectangle hits the entire axis of rotation wherever I put it. And so this is a disk. Basic form, the volume pi integral r squared. So now we'll put in the specifics. My rectangles go from this bottom starting point, which is a half, to this upper ending point, which is 3. The radius is the distance to the curve from the axis. That would be the distance to y equals 6 over x minus 1. However, these are y values. Again, I have to switch my function. So 6 over x minus 1, if I want to solve this for x, becomes y times x minus 1 is equal to 6. Or xy minus y is equal to 6. xy is equal to y plus 6. And so x is equal to y plus 6 divided by y. And so in this case, we get y plus 6 over y quantity squared dy. And I'm just going to set that up for time constraints. The last one, suppose I have same function, y equals 6 over x minus 1. And this time I want to go from the area y equals 0, x equals 2, x equals 4, and I want to do this about the x-axis. So the basic curve is the same, looks something like this. Y equals 0 is the x-axis. I'm going from x equals 2 to x equals 4, this region. And notice if I take my rectangle, it's now going vertically, and it hits the x-axis all the way across. This was 2 to 4. And so my volume is then going to be, again, disks, pi integral r squared. In this case, x goes from 2 to 4. My radius is the distance to the curve, which in this case is just 6 over x minus 1. Quantity squared, it's already solved for y in terms of x. And again, we can deal with that. But that is the setup for it.